Hello, and welcome back. In this video, we continue building on the previous lesson by exploring how loads, space types, and spaces are defined and used within the model. The goal of this part, just like the previous one, is to understand the tools, the logic behind them, and how they fit into the overall workflow. At this stage, we are focusing on learning the system rather than applying everything directly to the project file. In the next video, we will bring these concepts back into the sample model we have been developing and apply them step by step in a practical context. This approach helps ensure that you first understand what each tool does and why it matters, so when we return to the project, the process feels clear and intentional rather than mechanical. Let's talk about how lighting loads are handled in Energy Plus, and therefore in OpenStudio, because there are a few important things to understand. First important point. Energy Plus is not a lighting design tool. It doesn't simulate light distribution across a room. It can't tell you whether your luminaires provide enough foot candles or lux on the work plane. That job belongs to dedicated lighting software, like Dialux or Relux. What Energy Plus does very well is track two key things: the electric energy consumption of lights and luminaires, and most importantly, the thermal impact of that energy on the surrounding space. Every watt of electricity that goes into a light eventually turns into heat inside the building, or leaves through the return air, and that heat directly affects heating and cooling loads. Energy Plus also supports daylighting controls to automatically dim or switch off electric lights when enough natural light is available. We'll cover that in detail later. Now, back to defining lighting loads in OpenStudio. The most common way, especially for uniform overhead lighting like linear fluorescence or LED troffers, is to use lighting power density, or LPD. You enter it in watts per square foot, or watts per square meter. You see a typical example here, a value like 0.9 watts per square foot for an office space. This approach is perfect when you don't have a detailed fixture-by-fixture layout yet. It's exactly how most energy codes express lighting power allowances, ESHRE 90.1, Title 24, and others. For task lighting, think individual desk lamps. You often get better accuracy by defining the load as watts per person. And if you have a detailed lighting audit and know exactly how many fixtures of each type are installed, you can enter the rated power per individual unit, for example, 32 watts per recessed troffer, and then apply a multiplier to tell OpenStudio how many of those units exist in the space or space type. No matter which method you choose, per area, per person, or per unit, the actual power consumption at any moment is scaled by a fractional schedule, the rule set or other schedule we discussed earlier. This gives you full flexibility. You define the maximum possible load once, then use the schedule to model when and how much of that capacity is actually used, whether it's full on during occupied hours, 50% during lunch, or 10% overnight for safety lighting. One final key point about the thermal side. In Energy Plus, 100% of the electric energy consumed by lights is eventually rejected as heat to the environment. There's no useful mechanical work done, and almost no storage. That heat is split into 4 fractions that you can customize. Fraction radiant, long-wave radiation emitted to room surfaces. Fraction visible, short-wave radiation, the light you actually see, that eventually gets absorbed by surfaces. Return and air fraction, heat carried away by air leaving the space and entering the return duct. Important for plenum integrated fixtures. Fraction convected, heat directly warming the room air volume. You do not enter fraction convected directly. Instead, it is calculated automatically by Energy Plus as the remaining fraction, so that the sum of all heat gain fractions equals 1. Understanding this split is crucial because it changes how quickly heat enters the space air versus how much is stored in the structure. However, you can just use OpenStudio defaults in most cases. The Energy Plus input-output reference, which available online or in the documentation, includes typical fractional energy factors for different lighting categories in the Lights Object section. These are great starting points for the radiant, visible, return air, and convected fractions we talked about earlier. Here are a few examples. Incandescent lamps tend to have higher radiant and visible fractions. Fluorescent and LED fixtures often have more convected heat. Troffers with return air integration can have a significant return air fraction. Always cross-check these defaults with your actual fixture type. Manufacturer datasheets are the gold standard when you can get them. One important note: luminaires don't exist as native Energy Plus objects. They're a unique feature of OpenStudio's object. A luminaire represents an individual lighting fixture, a single troffer, pendant, desk lamp, and so on, and is defined by its lighting power per unit. The big advantage is you can position luminaires spatially inside a space. This isn't used for thermal calculations right now, but it's there to support future integration with radiance, for accurate electric lighting distribution and daylighting simulations in upcoming OpenStudio versions. Just like materials, constructions, and construction sets, both lights and luminaire definitions can be imported directly from libraries or the building component library. When you pull in a pre-built definition this way, you get ready-to-use power values and heat rejection fractions, super convenient. That said, always double-check those imported values against your project. Are the inputs realistic for your climate zone or building code? Do the heat splits match the actual fixture type? For reliable reference values, consult trusted sources such as the ASHRAE Fundamentals Handbook, Chapter on Lighting, and the Lighting Handbook by the Illuminating Engineering Society. Similar to lighting, Energy Plus does not model individual electric devices inside a space. In OpenStudio, you are not defining specific appliances. Instead, you are defining an aggregated electric equipment load. From a human perspective, a video game console and a toaster are very different. But for Energy Plus, they are treated the same way. Both are electric devices that consume power and release heat into the space. What matters to the simulation is not the type of device, but its behavior. Just like lighting, electric equipment can be defined using different calculation methods, such as power per unit floor area, or power per person, which you select directly in the electric equipment object. Unlike lighting objects, equipment objects in Energy Plus can use different fuel types, such as electricity, gas, steam, or other fuels, and each fuel type is reported separately in the simulation results. In this section, however, the focus is on electric equipment only. When you scroll down in the electric equipment object, you will see the fields that control heat transfer. These include fraction latent, which defines the portion of energy added to the zone air as moisture, fraction radiant, which defines the portion of energy emitted as long-wave radiation to surrounding surfaces, and fraction lost, which represents the portion of energy that does not contribute to the zone heat balance, either because it performs useful work or is rejected outside the space. You do not enter fraction convected directly. Instead, it is calculated automatically by Energy Plus as the remaining fraction, so that the sum of all heat gain fractions equals 1. People represent one of the most significant internal thermal loads in a space, but in OpenStudio they are modeled differently from lights or equipment. As with other internal loads, occupancy can be defined either by the total number of people in a space or by people per floor area, which represents occupant density. In addition to the number of occupants, the people object also describes how human heat is released into the space. A portion of the heat emitted by occupants is defined as fraction radiant, meaning long-wave radiation to surrounding surfaces. The remaining heat gain is automatically divided between sensible and latent components. Energy Plus performs this split internally based on typical metabolic behavior, so the modeler does not need to define sensible and latent fractions directly. In many practical models, the activity schedule is entered as a constant value, reflecting that the type of activity in the space remains the same, while the number of occupants varies throughout the day according to the occupancy schedule. However, the software allows much greater flexibility. The modeler can define short periods of increased or decreased activity, such as exercise, rest, or cultural behavior patterns, independently of how many people are present. Typical adult activity level values are available in reference tables and in the Energy Plus Input-Output Guide, and these values are used by Energy Plus to calculate the total heat gain from occupants in combination with the defined schedules. Water use equipment represents water consumption within a space for uses such as showers, cooking, and washing. In OpenStudio, water use equipment is defined using a peak flow rate, which represents the maximum water flow at the fixture. This peak value is then controlled over time by a flow rate fraction schedule, allowing the model to represent realistic patterns of water use. In addition to flow rate, a target temperature schedule is used to define the desired temperature of the supplied water. When entering a water use equipment object, these schedules appear directly in the data entry form and control how much water is used and at what temperature. How water heating energy is accounted for in the simulation depends on whether a water heating system has been defined elsewhere in the building model, which will be discussed in upcoming videos. If a heating system is present, Energy Plus achieves the target temperature by mixing hot and cold water at the fixture, and the required heating energy is tracked by the simulation. If the water use equipment is not connected to a heating system, the water is simply assumed to be delivered at the requested temperature, and the energy required to heat the incoming mains water is not included in the results. In both cases, total water consumption is still reported in the simulation outputs. In addition, any heat transferred from the water to the space is also accounted for. Heat transfer from water use equipment occurs through sensible heat addition to the zone air and latent moisture addition due to evaporation. Any remaining thermal energy is assumed to be carried away with the water and convected out of the space through the drain. For maximum flexibility, the fractions of sensible and latent heat rejected to the space are not entered as fixed values, but are instead controlled using a schedule. Water use equipment and its interactions with water heating systems will be examined in more detail later. Infiltration refers to outdoor air that enters a space unintentionally. This air comes through small gaps in the building envelope, as well as through doors and windows that are opened periodically. Because this air is not conditioned before entering the space, it can significantly affect both temperature and humidity. In contrast, design specification outdoor air represents outdoor air that is intentionally supplied to the building to meet ventilation and indoor air quality requirements. Even though the intent is different, both infiltration and designed outdoor air introduce heat and moisture into the space, and for that reason they are treated as thermal loads that must be handled by the HVAC system. In OpenStudio, infiltration is modeled differently from most other internal loads. Instead of being defined at the space level, infiltration is assigned directly under the Space Types tab. When working with a space type, you may notice that several different infiltration-related objects can be added. These include Design Specification Outdoor Air, Space Infiltration Design Flow Rate, and Space Infiltration Effective Leakage Area. Design Specification Outdoor Air is used to represent required ventilation rates and is commonly associated with ventilation standards such as ASHRAE 62.1 and 62.2, which focus on occupant health and comfort. The other two objects are alternative ways of modeling unintended air leakage through the building envelope. In most practical models, only one of these infiltration methods is selected for a given space type. The design flow rate method defines infiltration using a specified airflow rate, often adjusted by schedules and environmental conditions. The effective leakage area method, on the other hand, represents infiltration based on an equivalent leakage opening in the envelope, which responds to pressure differences. In the OpenStudio application, infiltration and outdoor air objects cannot be created manually from scratch. The only way to add them is by dragging the appropriate object from the library and dropping it onto a space type. Once added, the input fields become available for editing in the interface. Choosing the appropriate infiltration model and setting realistic input values is an important modeling decision, and additional guidance on these objects and their parameters can be found in the Energy Plus reference documentation. The Space Types tab is where common properties are defined once, and then reused across multiple spaces. When you open the general view, you can bring space types into the model directly from the library, or manage your own space types using the available buttons to create, duplicate, delete, or clean up unused items. In this view, each space type can be assigned a custom color for visual clarity, along with a construction set, a schedule set, and any relevant infiltration objects. These assignments are automatically applied whenever the space type is later assigned to a space. If no construction set is defined at the space type level, OpenStudio does not stop the model. Instead, it looks upward in the hierarchy and uses the construction set assigned to the parent level, such as the building story, ensuring that the model remains complete. When you click the Loads button at the top of the Space Types window, the interface switches to a detailed breakdown of all loads associated with each space type. Infiltration appears automatically once it has been assigned, and additional loads can be added by dragging load definitions from the panel on the right into the definition column. The schedules for these loads are inherited from the assigned schedule set by default, but they can be overridden when a specific load requires a different operating pattern. Both space type names and individual load names can be edited freely to match the modeler's naming conventions. Finally, for loads that are defined using individual rated values such as electric equipment or computers, a load multiplier can be applied. This allows a single load definition to represent multiple identical devices within the space, for example by using a multiplier to account for several workstations without redefining the load itself. When schedules, loads, and space types defined, the next step is to apply those space types to the actual activity areas within the building. Earlier, spaces were created using the Floor Plan Editor in the Geometry tab. Just as with thermal zones, the Assignment subtab of the Floor Plan Editor can be used to assign a space type to each space directly within the plan view. Space types can also be assigned from the Spaces tab. At first, this tab may seem redundant, since the floor plan editor already allows space assignment with visual feedback. However, the Spaces tab provides important additional capabilities. It allows you to edit multiple spaces on the same floor at the same time, and offers a higher level of control over the contents of each space. When using the Loads sub-tab within the Spaces tab, you can inspect all loads applied to each space and directly compare them with the original space type definitions. This makes it easy to verify that the intended loads have been applied correctly. One important visual detail in this view is text color. Loads inherited from a space type appear in green text, while loads defined directly at the space level appear in black text. This color convention is used throughout OpenStudio to indicate inherited versus user-defined data. In this same sub-tab, you can drag in additional loads that are specific to an individual space, even if that space already follows a space type. These added loads appear in black, indicating that they override or extend the inherited definition. Likewise, checkboxes next to inherited loads allow you to select specific items and remove them using the delete button. This demonstrates an important concept in OpenStudio. Space types are powerful tools for rapid assignment and consistency, but they are not restrictive. Individual spaces can always be customized when needed. The Surfaces and Subsurfaces sub-tabs further illustrate this inheritance logic. Here, constructions are automatically applied based on the assigned construction set and surface type. When necessary, a unique construction can be dragged in to replace an inherited one for a specific surface or opening. Another type of load that deserves special attention is the internal mass object. Internal mass can be added to space types just like other loads. Unlike people or equipment, internal mass does not consume energy and does not have an associated schedule. Instead, it adds thermal capacitance to the space, meaning it can store heat and release it over time. The thermal behavior of internal mass is controlled by its assigned construction and surface area. In spaces such as storage areas or warehouses with heavy shelving and stored materials, internal mass can have a significant impact on thermal performance. Internal mass objects are closely related to the Interior Partitions sub-tab. Interior partitions represent internal surfaces such as furniture or other large objects within a space. These surfaces do not define boundaries between spaces or between interior and exterior, but they can still participate in heat storage. When an interior partition is assigned a construction and the convert to internal mass option is enabled, OpenStudio treats it as part of the space thermal mass. The final sub-tab associated with spaces is shading. Shading surfaces play an important role in controlling solar gains and daylight availability, and their impact will be discussed in more detail in later chapters.